Hi, everyone. Welcome back. Our speaker today is Maria De-Arteaga. Maria is currently an assistant professor of information, risk, and operation management at the University of Texas at Austin, where she is also a core faculty member in the Machine Learning Laboratory and an affiliated faculty of Good Systems. She holds a joint PhD in machine learning and public policy, a master's in machine learning, both from CMU, and a bachelor's in mathematics from Universidad Nacional de Colombia. Maria's research focuses on the risks and opportunities of using machine learning to support experts' decisions in high-stakes settings, with a particular interest in algorithmic fairness and human-AI collaboration. And today she will tell us about characterizing algorithmic unfairness from compounding injustices to social norm bias.
Thank you very much for the introduction, and thank you everyone for being here. We're not a huge group, so feel free to jump in at any point with questions, comments. I'm very happy to make these very conversational. And yeah, so my research broadly focuses, as I was saying, on the risks and opportunities of ML in high-stake settings, especially when we're using it for decision support. And so as part of this, a lot of my work has been focused on characterizing risks of algorithmic fairness. Based on these, I work on how do we mitigate these risks. And I've also focused a lot on understanding how is it that humans make use of ML tools, and grounded on that understanding, how should we be designing these tools so that they're better team members, rather than thinking about the task as a prediction in isolation. And today's talk will be focused on the first component that I just mentioned, that is, how do we characterize risks of algorithmic unfairness? And as you'll see, a common thread through it is understanding what is the concern that we have. What is it grounded on in terms of how social scientists have thought about risks of discrimination and unfairness in the absence of algorithms? And then how do we measure this? How do we quantify it? And how do we move forward from that? So an example that will be anchoring today's talk is the use of machine learning in hiring and recruiting pipelines. So we've seen in the past years a huge increase in the conversation and now also in the deployment of machine learning tools to assist both recruiting and hiring. And there's a lot of concern around these about the risks of potential biases. But there's also a lot of optimism about this, of people saying, well, the process is already so biased, maybe this can actually help us improve it. So what is the type of concern that we may have when we're building a tool for recruiting, for example? Let's say that we're recruiting a computer programmer. And so we want to find someone, for instance, that is a software engineer who has experience in Java, Python, C++. And naturally, we wouldn't want things like the fact that their name is Jane to influence the likelihood that we see this candidate as a likely candidate in our search. The risk and the challenge here is that even if we obfuscate the information that is evidently informative of the person's demographics, then there may be information such as the fact that someone was a softball team captain at a historically Black college that may lead the algorithm to infer that they're likely a Black woman. And this is a problem that is increasingly complex as the data that is used to fit these systems is more and more unstructured. These are the collaborators of the first work that I'll be presenting today. So an example of this is our online presence. And a lot of us receive emails of this form, oh, I saw your website and I think that you may be interested in this. And a lot of these emails are either automated or could be easily automated. You read them and you say, okay, I could see writing a script to do this automatically, right? And so In collaboration with researchers at LinkedIn, and while I was spending some time at Microsoft Research, we asked, what are the risks when we're using AI for automated recruiting? And this is work that we published at FACT a couple of years ago. And here we said, well, what is the easiest task that we need to solve if we want to do automated recruiting? There's a lot of different prediction tasks, right? What is this person's occupation? How good are they at their job? What is their potential to grow? How well are they going to fit in a team? There's really a lot of constructs that are of relevance. And we said, let's focus on the simplest one, that is, what is the person's occupation, right? So we have 400,000 online biographies that we collected through Common Crawl. And we did this using regular expressions. And so the regular expression has the form that is highlighted there. So it's two words that are capitalized, is a, and then maybe a word title, a title that is from the Bureau of Labor Statistics, and then he, she, and it goes on. So it's written in third person. So the fact that it's written in third person allows us to know the gender so that we can then do assessment on potential gender biases. The first portion of the research has the limitation that we only considered binary pronouns, and so it's limited to only he and she. In the latest part of this research, we did a follow-up in which we manually added a data set where we assessed they being used in singular. And so we expanded it to these, but for this first portion, it has that limitation. And here the classification task is predicting the title out of 28 options of the Bureau of Labor Statistics from the text in the biography, naturally dropping the sentence that contains the title, right? So we would be using in this example, the orange text to predict that this person is a professor. So to give you an idea of the distribution of our data set, there is a lot of different occupations ranging from yoga teacher to psychologist to professor. As you can see here, us professors have really like having our biographies online. Obviously, there's also the way that we collected the data may be a better fit for how professors write their biographies. So this is the data set that we have. And we consider a learning pipeline where we vary what is the semantic representation and the learning algorithm that we use, ranging from the simplest form of having a bag of words with a logistic regression. This has the particular advantage of not having a second source of potential bias of using any form of pre-trained embedding, because if we're using a pre-trained embedding, then there's the question of where is the bias coming from? Is it coming from the representation or from the supervised learning stage of the pipeline? One thing that we played around a little bit, but I won't present, is we also looked at what happens when we use the biased word embeddings. But so we play with what happens when we range from bag of words to logistic regressions to a word embedding with a deep neural network. And in the latest version that I'll show, we also look at contextual word embeddings. And so we have the biography, we have a semantic representation and a learning algorithm, and the task is to predict the occupation. So this was my biography at the time that we did this research. And so if I input my biography in the neural network, it would predict that I am a teacher. And you can see it's a network with attention, so you can see the words that it's paying attention to. And motivated by the research by Bertrand and Mullainathan, who many of you may be familiar with, where they looked at what happens when you send CVs with different names such that the names are indicative of different demographics, and how does that change callback rates? We asked the same question for algorithms. And so we said, how will the predictions change if explicit gender indicators are swapped? An important thing here is being careful on what is it that this question is allowing us to answer and what it is not allowing us to answer, right? This is not a counterfactual on what would happen if a sensitive attribute were to change, because then many other things would change with it. This is just allowing us to see what is the effect of these particular features on the predictions, right? And so we think of it as analogous to Bertrand and Mullainathan's experiment on callback rates on CVs, where you just swap the name and leave everything the same. And in my case, for example, if I were to use male gender pronouns, it would predict that I'm a software engineer, not a teacher. And this is something that happens at a scale. So what we're seeing here is cases where the prediction is incorrect with the person's pronouns, but would be correct if they were using different pronouns. So for instance, women rappers are very often incorrectly predicted as models, but would be predicted as rappers if they were using male gender pronouns. Meanwhile, men who are paralegals are incorrectly predicted to be attorneys, but would be correctly predicted to be paralegals if they were using female gender pronouns. One of the important things that this question allows to answer is maybe if we're having gaps in predictions, it's just because there's one group that writes biographies that are very cryptic. Like maybe it just happens to be the case that men paralegals write biographies as if they were attorneys. And so seeing what would happen when we do this swap allows us to say, okay, it's not just a matter of all of the writing being fundamentally different so that the prediction task just has no hope, right? So here we see that there's something going on, but naturally, well, maybe we can just scrub the explicit gender indicators and be done with it. So what is happening beyond gender indicators? Here we focus on the gender accuracy gap. So what we're seeing here is in the x-axis, we're seeing the percentage of women in each occupation. And in the y-axis, we're seeing the gap in true positive rates. So if there were no gaps, so as an example, if we look at surgeon here, right, approximately 15% of surgeons in our data are women, and the true positive gender gap is negative, meaning the true positive rate gap for men is higher than for women, right? So if we didn't see gaps, we should see things around the horizontal line here, right? Or at least scattered with some noise. What we see is very different from that, right? What we're seeing here is that for occupations that are predominantly male, then the algorithm is more accurate for men. And for occupations that are predominantly female, the algorithm is more accurate on women. This is statistically unsurprising. You have more of one group in one occupation, and so statistically, you're going to say, well, I think this person is more likely if I predict that this person is in healthcare, for example, and so we can see that there's a number of healthcare occupations, right, like surgeon, physician, nurse, then you can use gender inference to say, well, are they more likely to be a surgeon or a physician or a nurse, right? So if this is not statistically unsurprising, why should we care about it? Why is it a problem? It is a problem because it means that we may be compounding imbalances. So this is an informal version of our theorem where what is happening here is that if the fraction of women in an occupation is less than 50% and the gender gap is negative, then the fraction of women in true positives is less than it originally was in the data set. Why is this a problem? Why are we thinking about true positives? First of all, let's go back to the task that motivated us. We're predicting someone's occupation to decide whether we target them with a job ad, for example. Naturally, I'm only going to benefit from job ads that I am qualified to do. If you show me a great job for a physician position, I'm not suddenly going to have a medical degree to apply to it, right? And so the true positives here are really important because those are the people that stand to benefit from seeing this ad. And what we relate these to is the notion of compounding injustice. So in indirect discrimination, Deborah Hellman has termed the notion of compounding injustice that says that if the initial imbalance constitutes an injustice, then if the model's prediction is informed by and compounds that injustice, then that would constitute indirect discrimination. So in cases in which the initial gender imbalance in an occupation constitutes or is a result of injustices, then the fact that the model is making use of that imbalance to then inform predictions that compound that constitutes a compounding injustice, which would be under this framing a form of indirect discrimination. So let's look at a concrete example of what happens when we talk about compounding injustices and compounding imbalances. As I said, in our data, approximately 15% of surgeons are women, so 14.6%, right? But when we look at the recall, at the true positive rate, it's 71% for men and 54% for women. So when we look at the pool of surgeons who would be seeing an ad for surgeon, for instance, then only 11.6% of them would be women. So we have this compounding gap, right? And you can see how if you encounter multiple algorithms with this property throughout, then you can have what we would term a leaky pipeline effect, in which at each stage you're having less and less of a group. I see a question, Elliot.
Hi, so I'm just curious in terms of the theorem, what is assumed about the classifier's behavior? Like, are you assuming that it's Bayes optimal with respect to the training data?
Here, we're just saying if you have the fraction of women being less than 50%, and you have this property in the true positive rates, right? So you're not assuming anything about the classifier.
But
whatever the classifier is.
A property of the predictive model rather than the data set?
It's gonna depend on both, right? But we're not saying, okay, this is the property of the predictive model that will yield this type of true positive rates. We're saying, if you have this type of imbalance in your data and you have this property of your algorithm, then you're going to have a compounding imbalance effect.
So what is the property of the algorithm? Maybe that's the question I'm asking.
The true positive rate. We're not saying when is it that this true positive rate is going to be negative. We're saying if you have this true positive rate, then you're going to have a compounding imbalance effect.
Okay, thank you.
So this is something that we see throughout the different learning algorithms and semantic representations. So what we're seeing here is in blue, it's what happens when we have the entire biography, well, excluding the first line, right? And then what happens when we scrub explicit gender indicators. And there's two things that are worth noting here. In the bottom right, you see the overall performance of the method. So the first thing we see is that there's not a significant decline in accuracy overall when we scrub the explicit gender indicators, but we do see that the compounding effect, imbalance effect, gets mitigated, right? So we have an instance in which we can improve on a notion of fairness that we care about without necessarily giving up on accuracy. And this is a topic that I'll get back to later in the talk. But we also see that the effect is not fully gone, right? And we see that there's still, when we scrub explicit indicators throughout all of the representations, we see that there's still a compounding effect, right? And we can think of these as analogous to what happened in orchestral auditions, where at some point they decided to ask people playing to play behind a curtain. This was primarily motivated by wanting to mitigate racial biases so that the people in the jury wouldn't be able to tell the demographics. And when they did this, they found that this approach was not very effective to mitigating gender biases because people could still hear the shoes. And often they would hear heels, and then they would be able to infer that the person playing was likely a woman. So this is analogous to what we're seeing in the algorithm, right? Where there's still this signal that the algorithm is picking up on. And everything that I showed you is in a data set that we constructed so that it's, and by the way, the data is, the code to reproduce the data set is publicly available. So this allows us to have something where we have a lot of control over the data and the outcomes. But it's something that we've seen in many different headlines and instantiations, right? Ranging from Amazon scraping an AI recruiting tool to other domains, like, for example, Google labeling people's occupations, right? And so there's people who have highlighted the fact that when you look at neuroscientists, for example, famous women neuroscientists tend to have labels that are on the line of educator, whereas men have labels that are on that emphasize the fact that they're neuroscientists. Elliot.
Sorry for the repeated interruption. Could you say more about how the gender pronouns are removed? Do you replace it with a gender neutral pronoun like they? Do you just remove
them,
those tokens, or sorry?
Yeah, just remove them. Which for the representations that we're using here, because the order doesn't matter, then it's not a huge issue. Right?
I see. Okay.
Yeah.
So I guess that plot that you showed was from the bag of words model rather than the attention-based model that you had showed a qualitative result of before.
No, we have all of them.
Okay. Okay, cool.
We have all of them. So we have the bag of word with the logistic regression, the word embedding with the logistic regression, and the word embedding with the neural net. Sumega.
Yeah, so in for example, in the orchestra example, they did remove, I think with carpet or something, it was the bias was even decreased. So do you have that example? How can you even decrease the bias more?
Yeah, so we'll get into how do we mitigate that problem in a second. This question is a great opening for the next part that we'll be discussing. Exactly. Yeah, so the question is, so the key takeaways are, the first one is very straightforward, right? Scrubbing explicit gender indicators is not enough. That is not unsurprising. There's correlations. And while we often have a narrative of AI reproducing biases, something that we emphasize in this work is the compounding effect. So it's not just a matter of reproducing biases that are in the data, but it's a matter of compounding these. And this is something that we can very directly link to notions of indirect discrimination, not just in terms of the effect, but in terms of the mechanism, the fact that this effect is a result of the algorithm making use of that information to inform the prediction. So with this, we get to the question that we were just talking about, of how do we address the problem? How do we roll out a carpet, right? And there are tons of approaches now. So I'll briefly talk about an approach that we proposed in later work, and then I'll talk a little bit more about the different approaches that have been proposed, and also what are some of the residual harms of these group fairness approaches. So in our work, what we ask is, can we use bias to fight bias? So in work that we published at AIES, we studied biases present in word embeddings. And at that point, there had been really cool work, some of it by the co-authors of this work, actually. So this work that we published at AIES. So for instance, Adam had already previously done work looking at, if we're concerned with a certain type of bias, with gender bias, for example, is that a bias that is found in the word embedding? What we were interested in doing in this work was, if we don't know a priori what is the bias that we want to look for, is there a way to probe to see what are potential biases that are encoded in this word embedding? And that is something that is particularly important if we're thinking about the fact that when we shift context, the types of biases that are salient may be different. So if we suddenly start looking at word embeddings in Spanish, then the type of social constructs that inform different forms of systemic discrimination and biases may be different to the ones that lead to biases in a corpus in English, where documents are primarily sourced from the US. So we ask, can we detect biases in word embeddings? And we proposed an algorithm that allowed us to basically enumerate potential biases. And then we did an assessment where we showed that the biases that popularly used word embeddings contain were associated to people's names and aligned with societal stereotypes. So to give you an example, you would have things like a cluster of Latino names would be associated with things like drug smuggler, illegal, and undocumented, and things like that. So having done this work, we asked, can we use bias to fight bias? So the underlying idea of this research was we can summarize it in this portion of Shakespeare's Romeo and Juliet, that is, what's in a name, right? You don't want the fact that I am, for instance, if I'm predicting that whether someone's an engineer, whether their name is Jane, I don't want that to influence my prediction, right? And that is something that we can actually enforce mathematically, right? So this is work that we published at NACL. And what we can do here is we can say, well, I'm going to penalize correlations between errors of my prediction and locations of the name in the word embedding, right? So I have two components. I have the embeddings of the names, then I have predictions. And I say, if the likelihood that I correctly predict this is correlated with where the name of that person lies in the word embedding, then I'm going to penalize that, right? I can do that during training, and then at prediction time, I don't need to have names. One of the advantages here is that while I do need to have names, we don't need to have access to sensitive attributes. And this was something that was largely motivated by our research, the first portion of the research, where the way that we collected the data allowed us to have gender information because we constrained ourselves to biographies written in third person. But if we have a biography written in first person, we don't have that information. And there's a number of reasons why we wouldn't want to just infer that information from the biography, right? So what this allows us to do is it allows us to not have to rely on having access to sensitive attributes. And it actually allows us to mitigate multiple dimensions of bias at once. So the way that we do this is, well, typically we're minimizing a loss function, right? So let's say a cross entropy loss. And so we propose a regularization term where we have two variants. One is based on, it's a cluster constraint loss. So we first cluster the names in the word embedding, right? And then we penalize if there are disparities in the performance across different clusters. So if I'm doing much better at predicting the occupation for one cluster than for the other, right, and I do that by occupation, then I penalize that. This has the disadvantage of relying on an intermediate step of clustering. So we can also do that directly, right, and directly penalize the covariance. So I can directly penalize the covariance between the location in the word embedding and whether the prediction is correct. And so we first do results on a semi-synthetic data set where we had control of everything that was going on. And so here we can have what happens when we have an unconstrained loss and what happens when we tightly constrain it, right? So naturally, the more we constrain it, the smaller the gender gap. One very important thing that we see here, again, is that we can make a lot of gains in mitigating the gap without giving up on accuracy, right? And this is something that, again, in terms of going back to the narratives that we often have about the relation, different properties of what is happening when we're concerned with algorithmic fairness, what happens when we enforce constraints. Often we have cases where we can significantly improve in terms of a fairness measure that we care about without sacrificing accuracy. And this is something that can happen for a number of reasons. The most obvious one is the fact that often we're not optimizing an objective that is strictly convex. And so there's more than one solution that can yield the same performance. But if we don't explicitly encode that in our objective, there's no reason why we would get the one that has the benefits from the fairness perspective. So I just showed you one approach that we propose. One of the key differences between our approach and other approaches is the fact that we don't rely on access to sensitive attributes. But there's a ton of different approaches. And so have we fixed the problem? Did we roll out a carpet that makes it impossible to infer information about demographics? And if so, which approach should we choose, right? There's the type of approach that I just showed you, where we don't have access to sensitive attributes. There's pre-processing approaches where we're manipulating the data beforehand. There's other in-processing, this is an in-processing approach, the one that I just showed you. There are other in-processing approaches where I may mitigate other types of gaps that I care about, in particular, just group fairness gaps, there are post-processing approaches. Post-processing approaches have been particularly popular for a number of reasons. The first one is, well, they're just so nice to implement. They're so easy to implement. If you're thinking about a deployment, it's very different to have to change a bunch of stages during your pipeline that may even involve different teams in the production and deployment versus just having to change something at the end, right? So not having to not just retrain, but change many different elements is something that is really beneficial. And it's very rare for companies to be open about what exactly they're deploying, but from time to time we have that. And for instance, LinkedIn has shared that they've used post-processing approaches to improve their search algorithms, right? So the question here is this enough, right? It is great that we've made progress here. It's great that we have mitigated the problems. Are we done? Is our work right now to just try to make sure that everyone's using these, or are there issues that we're not seeing? And more importantly, are there issues that we're invisibilizing? So this is the work of research that we published earlier this year on social norm bias, led by a now PhD student, Myra Cheng, when she was an intern at Microsoft Research. And what we mean by social norm bias is that the associations between an algorithm's predictions and adherence to social norms. So we look at how is it that the algorithm's predictions relate to existing social norms. And we argue that this is a source of bias that is overlooked by common group fairness approaches. So this again is something that we anchor on existing research on discrimination. And in particular here, we focus on workplace discrimination. So Madeleine Hellman, not to be confused with Hellman, Deborah Hellman, has done work on descriptive and prescriptive stereotypes. So descriptive stereotypes are stereotypes that are attributes that are believed to characterize a group. So for instance, attributes that are believed to characterize women. And here, descriptive stereotypes lead to if there's a perceived lack of fit between a group and a certain job, for example, if you display descriptive stereotypes that can exacerbate bias against you. So an example of people trying to avoid the harms associated to descriptive stereotypes is women saying, well, maybe I'll wear a pantsuit and not a dress to give a talk. Or there's a ton of workshops that you go for instance, women in the workplace, where they tell you whatever you do not bake cookies and bring them to the office, right? So that is descriptive stereotypes. It's saying if you display these behaviors that are thought of as stereotypical to your group, that may harm you. There are also prescriptive stereotypes that are how people think that you ought to behave. And so an example of prescriptive stereotypes are, for instance, why women who are highly voluble tend to perceive negatively, whereas men aren't, right? So if you're very highly voluble, then people will say, well, you're just very aggressive, or you're just very bossy, right? So you have both sides. You have descriptive stereotypes and prescriptive stereotypes. In this work, we ask, well, do algorithms exhibit bias based on descriptive stereotypes? And we term this social norm bias, right? So do algorithms exhibit bias based on how much a person adheres to norms that are thought of to be determining of their group? So to study this, we have an occupation classifier. We've talked a bunch about that. Then we say, okay, how can we measure inferred gender norms that are inferred by the algorithm? And then we look at the correlation between these two. So we've talked enough about the occupation classifier. Here we change a little bit the architecture to modernize it a little bit and use contextual word embeddings. Then we move on to measuring inferred gender norms. So how do we do this? We train a classifier to predict the gender pronouns, and we interpret the predicted probability as a measure to adherence to the inferred masculine or feminine gender norms. So the first question there is, what are the potential harms of correlating with inferred gender norms? So the first thing that we assess is that these inferred gender norms are correlated with societal gender norms. So these, what we're seeing in this plot, is human labels for how gendered certain terms are. And then in the y-axis, we're seeing the weight in a predictive model. This is just a regression in this case. And here what we're seeing is that there's a very strong correlation, right? So the words that the algorithm perceives as more feminine or less feminine, most masculine here and most feminine here, are also words that people tend to perceive in the same way. Some outliers are interesting to see, for instance, child, which makes a lot of sense. Once you realize that what is happening here is that child, we don't think of it as a gendered term, but in biographies, women tend to mention child a lot more than men do, because they tend to mention family more. So once we have this measure of inferred gender norms, and we know that they correlate with societal gender norms, then there's a risk of compounding harms and perpetuating social bias if the algorithm is making use of these social norms to inform its predictions, right? So we then look at the correlation between these two. And so what we do is we take the subset of occupations that have the pronoun she, so we're just looking at this subset, and we look at the Spearman correlation between the prediction of the occupation and the prediction of the pronoun. So if you have a positive correlation, it means that biographies that are inferred to be feminine are rewarded by the occupation classifier. And negative correlation means that biographies that are inferred to be masculine are rewarded by the occupation classifier. And here we look at the correlation for each of the occupations, right? And then we look at the correlation of those correlations. So what we see here is, again, occupations that are predominantly masculine. In this case, biographies, remember that this is just biographies with she as the gender pronoun. Biographies that are inferred to be more masculine are rewarded by the classifier, whereas biographies in the case of occupations that are predominantly feminine, well, not feminine, because that's multiple dimensions of gender, but predominantly have women in it, then the predictions that are thought to be where the algorithm infers that someone is very feminine, then they're more likely to be predicted in this occupation, right? So the strength of the correlation increases with the occupation's gender imbalance. And this is a problem. Let's look at an example of social norm bias in the algorithm. The word empowerment, for example, is associated with inferred feminine norms by the algorithm. What this means is that using the word empowerment in a biography leads women surgeons to be less likely to be correctly classified as surgeons. And we then look at what happens with this correlation when we implement different types of bias mitigation strategies. So post-processing is exactly the same, has exactly the same amount of social norm bias as not doing any type of intervention, right? Because in post-processing, we're not changing the within group ordering. So the social norm bias stays exactly the same. We see that there's different approaches that do mitigate the problem. But it's not something that because we mitigate group fairness, we have mitigated the problem, right? And so here we see that first, we do have these correlations persisting after we use this type of interventions. And as I was saying, post-processing doesn't mitigate these at all. So to summarize, what we find here is a number of things. First, we find that algorithms may display what we term social norm bias. And again, this is tightly related to notions of discrimination that are already present in our society, and in particular to discrimination on the basis of descriptive stereotypes. And in particular, when we look at different types of group fairness approaches, they're very different when it comes to social norm bias. And there's two key things here to take away. The first one is that there may be a lot of reasons to incur in the cost of retraining, because post-processing approaches in particular don't mitigate this type of bias at all as a result of keeping within group ordering the same. And when it comes to in-processing approaches, for instance, they can be very different from each other. So we cannot take for granted that because we use an in-processing approach, then we have mitigated social norm bias. It's something that we need to explicitly assess, because it's not something that has an inherent correlation with the mitigation of group fairness, of group unfairness. And finally, something that is very related to what I just said is that if we just measure fairness at the group level, we may be dealing harms to individuals. This is something that has been discussed by other researchers, in particular researchers of philosophy of AI, like Lily Hu, right? And this work constitutes a concrete instantiation of what is a type of harm that we're missing when we just consider group fairness approaches and why these socially salient. And with this, I'll pause here and open for any questions that you may have. Thank you, everyone.
Thanks, Maria.
Yeah, thanks for the great talk. So I didn't understand completely your point. Second point, can you briefly describe it again?
Yeah, the one on post-processing?
Yeah.
Yeah, so what is happening in post-processing is that you train a model, right? And then you take your predictions of that model. And there's different post-processing approaches. The most straightforward one is to say you have some constraint on, for instance, wanting to equalize false positive rates. And so what you do is you use different classification thresholds for the two groups, right? But what happens is the within group ordering is staying the same. If I was more likely to be predicted as a professor than another woman, then I'll still be more likely to be classified as a professor than that other woman after the post-processing approach, right? That within group ordering stays exactly the same. So as a result of that, because what the social norm bias is measuring is the correlation between how likely you are to be predicted to be in your occupation, right? With how likely you are to be predicted to be in the majority group in that occupation, then using a post-processing approach is not going to change that correlation at all. And so the issue there is, if your initial prediction had social norm bias, if your initial prediction was saying, well, I'm going to predict that you're more likely to be a surgeon if I perceive you to be masculine, or I'm going to predict that you're more likely to be a software engineer if I perceive you to be masculine, then that property is still going to be a property of your algorithm that does hold a group fairness metric.
So, sorry, I have a follow-up question. So there are works on considering like multiple groups at the same time. Do you think that like, okay, yes, I understand that everything cannot be decided by this, but maybe there is some like, there is some other feature that is also distinguishing between these two women, and then if you have fairness based on that feature too, then this effect might be
yeah. So that is why we see that, for example, in-processing approaches typically mitigate this more, right? Because in processing, what you're saying is, I'm going to penalize it if your classification displays a certain type of error. So let's think about, for example, and I didn't include it in these results, but we did include the method that I presented earlier today in the results of the paper. So let's think about that approach, which is similar to other group fairness in processing approaches, where you say, I'm going to penalize your classification if you display a certain property, right? Then what is going to happen is that you may be nudging the algorithm to make use of other correlations, right? And once you break the reliance of the algorithm on correlations that depend on that are very correlated to the sensitive attribute, then you can gain a lot of improvement in terms of social norm bias. So the work that we do here is somewhat related to work that Zach Lipton and Alex Sholoshova did, looking at the disparate impact on disparate treatment, right? And in their work, they just look at anything that any group fairness approach as kind of being equal, right? One of the things that we see here is that when it comes to social norm bias, you actually have very stark differences between different approaches, and in particular in processing and post-processing. So to your point, in processing can get you a part of the way in mitigating social norm bias because you're penalizing that correlation, right? When I say, okay, don't make a prediction that leads you to be really good at classifying men as surgeons, but not women, then the algorithm is less likely to say, well, if you mentioned that you had kids, then I'm going to predict that you're probably not a surgeon, right? And so that breaks reliance on descriptive stereotypes. That's not a given, which is why we need to assess it, right? And you see here how there's certain types of approaches that could have that are very different, but you do get a big portion of the way by incurring in, you potentially get a big portion of the way by incurring in the retraining and in processing versus post-processing.
Okay, yeah, thank you.
Elliot.
So yeah, this question brings up a kind of a tricky topic. If you don't think it's an interesting question, feel free to just say so and not answer it. But I'm kind of curious to hear your thoughts on thinking about social norm bias and its relation to causality as a potential framework for analyzing these fairness concerns. So
yeah,
okay, if that like brings up something, just go ahead and respond. I won't qualify it further. Thanks.
No, sorry, I didn't mean to interrupt you. Did you want to share a little bit more before I jump in?
Okay, yeah. I mean, so I'm just thinking like in kind of vanilla fair classification, if you like, there's interpretations of the correlation of the sensitive attribute and the target label as a kind of a data confound. And what you're looking for is a type of representation or classifier that somehow removes that confound and predicts according to sort of an ideal world where these things are not correlated. And I was thinking about that in terms of the social norm bias, because it seems like you might interpret the social norm issue as a type of a confound on the data, but it's a lot trickier to remove this. And I think, yeah, I was interested by the way that you showed how it could be addressed, but I'm also open to you telling me you don't think causality is a useful framework for this, but just kind of curious to hear your thoughts about the connection there.
No, I think that's a great question. And I think that conceptually, it is likely a good framework for it. We haven't done any experiments with that type of approaches. I think that in particular, examples that look at which are admissible pathways versus not admissible pathways would likely help you mitigate social norm bias, because the reliance on a descriptive stereotype, you could think of it as an inadmissible pathway, right? Because in these applications and a lot of other applications, there you would need a knowledge of the causal graph that you don't have, then that is why in practice I am skeptical that causal approaches are going to help us mitigate it, just because having knowledge of these causal graphs so that we can penalize for pathways that correspond to descriptive stereotypes, I think is unlikely to be feasible. But conceptually, I do think that a causal framework is a great way of further characterizing what we mean by social norm bias.
Okay, great, thanks.
Any other questions?
Okay, I guess there are no more questions. Thanks again for coming to the seminar, Maria. It was wonderful.
Yeah, thank you all for your time. And thank you.